Hey everyone, Michael Unger here with another edition of Ask an Astronomer. And as always, we are here with our fabulous astronomer, just a couple doors down from me on the unceded territory of the Musqueam, Squamish, and Tsleil-Waututh, and that is Marley Leacock. Hi, Marley. How's it going?
Good. It's good. How are you?
I'm great. This is my time to shine. I love fall because I can finally breathe and think again because it's not so hot and the cooler, a little bit of a wind blowing in. I can maybe wear some sweaters, a jacket. I'm back to wearing jackets. I just feel more myself during fall, so I'm great.
That's good. No, you love a sweater. I have noticed this. Michael loves a good sweater.
It's true. I just, sometimes there's just periods of years that you're just like your complete self. What would be like your complete time of year?
I don't know if there is a time of year. I'm always mildly uncomfortable. I think no matter what the weather's doing.
Well, you're from Calgary, so it has like those huge shifts, right? Like it's
Yeah.
really hot in the summer and then really cold in the winter. So
Yes.
is there even a proper fall?
Not really. It'll just be warm, 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 and then it'll start snowing. Is for what I remember most of the time. Usually by Halloween, you're in snowsuits because it's snowy and it's cold usually by then. So there's not a proper, the leaves don't really fall. Like it'll change the color and fall down. They just accumulate a lot of snow and they just fall off and become mush and then covered by snow. That's kind of what I remember. So I don't think there's ever been a time where I've been happy with what they're doing. It's either too hot or too cold.
Well, there you go. If you are either too hot or too cold out there, but you have a question about anything under the universe, you should throw it into the chat if you're watching on YouTube or if you're on Facebook. Because you know what? During our last episode, we had a question that came in just before we ended, and it was actually a really good question. In fact, it was such a good question. We are going to dedicate the entire episode to that one question. So get in and maybe ask a question for the future episodes. So Marley, for this episode, we are going to focus in on something that we are, of course, talking a lot about this fall. We're talking about the moon. You were talking about the moon in the last episode, and you were talking about, of course, in relation to the Chandrayaan-3 mission. And lots of missions going back to the moon and rovers having to survive the day, but also the night, which has these huge temperature shifts. Question came in, could humans survive the lunar night?
Yeah, when you asked me it after we finished 2 weeks ago, like, could humans survive lunar night? And my first response was just no. Like, that's the gut response was like, no, I feel like we couldn't do that. But then I started thinking about it a bit longer, and I was like, well, how, like, instead of no, like, how could we, right? Because if I'm assuming the answer is no, well, then how could we possibly survive the lunar night? And then that kind of led me down a spiraling rabbit hole of like, well, what exactly is going on at lunar night in terms of all the stuff I talked about with, heat and the length and rovers, but moving that over to human beings. And so I wanted to, well, actually, I kind of just forced us to end up talking about this the whole episode because it goes in a lot of different directions, really, is could we survive the lunar night? Well, really, if we took any human being and just put them on the moon, they're not going to survive, right? There's no atmosphere. There's nothing there for us to be able to survive. It'd be pretty terrible, honestly. So instead, I wanted to look at it in the focus of like a mission, right? So what are we expecting to have if we're going to go to the moon, and could we maybe do it on lunar night? And so that kind of led me in three different directions. And these three different things all kind of affect one another. And so we have to think about, well, where are we landing on the moon to survive lunar night? Because the moon is not just like Earth, is not the same all over, right? You have different weather patterns at the equator than you do up here or even here to Calgary. Like, there's different. The moon is the same, right? Like there's different things going on, different places on the moon. And the two things that kind of follow out of where are we landing, where are we going to be on the moon are what temperatures can we expect to see in those places and how much sunlight do we get? And those two things play hand in hand, but there's also a lot of sub characterizations that go on from both of those. So those are kind of our three main questions that we have to deal with when we're thinking about at least that I started thinking about with could humans survive lunar night?
Right. And I think that's interesting to think about. I've never really thought of different locations on the moon kind of being the same, how there's the weather is different in different locations on Earth, because we have an atmosphere. And of course, that is changing the weather patterns, but there's not really any weather on the moon, right?
No, not really. But the moon's got, well, there's no weather. The moon's got a lot of different stuff going on in terms of terrain and everything like that, right? The moon is a very dynamic, well, very interesting surface to look at. There's a lot going on. Even you look at the near side of the moon compared to the far side of the moon, it looks like two completely different objects, right? So there's all these different things to consider and how sunlight interacts with the terrain and stuff like that, which we get into. But really, what this question took me all the way back to the Apollo missions, because I started to think about, well, where did they go during Apollo? Like, where did they land? Of course, it was all on the near side of the moon. But what I wanted to think about was, well, what time of day are they landing on the moon, right? They weren't there for very long, right? Never very long on the surface of the moon. I think the maximum was like 50 or 70 something hours on the surface of the moon. And of course, lunar day along the equator, which is where a lot of these Apollo missions landed in and amongst the equator of the moon. They were always like, what phase? Like, when were they going? Right? What was going on with the moon at that time? So NASA actually has this video, which always plays really poorly in the beginning, that shows the phase of the moon at each time they landed. So Apollo 11, it was just about first quarter. It was actually 2 days before first quarter of the moon. So this would be early in the lunar day. A lunar day, of course, being 2 Earth weeks, right? So very early in lunar day is when they've landed for Apollo 11. We skip a couple months and we hit Apollo 12, which is a bit closer to, we're in waxing gibbous, about 4 days before the full moon. So maybe like midday lunar day, right? We have a slightly different amount going on. I love this video because it shows the wobble of the moon, which is very fun, and we get to talk about it a bit later. We skip Apollo 13 because that didn't land on the moon. We get to Apollo 14 a few years later in 71, and we have them landing in, again, kind of a waxing gibbous, right? 5 days before the full moon. So we're, again, kind of similar times of day, lunar day, for all of these different missions. And this continues for the rest of the Apollo missions. Apollo 15 actually landed on the day that first quarter occurred, right? So sunrise, I guess. This is a very long skip. Apollo 16, again, was also on first quarter moon, and Apollo 17 was 2 days before the first quarter. So you sense a bit of a theme, right? They all stay pretty close to the equator in location wise, but they are also there kind of early in the lunar day, which I know is weird to think about because early in the day for us is very different, but early in the lunar day, when the sun is just rising. And you actually see that reflected in the images that are taken from the Apollo missions, right? So these are both from Apollo 11 because I like that one the most, I guess. I don't know. I just picked them. And you end up seeing these long shadows across the surface, right? Kind of how you would see them at sunrise on Earth, right? When the sun's first coming up, your shadows stretch along the surface. They're very, very long. And you get these long stretches, right? Kind of signifying early in the day. And so that made me think about, well, how hot is it then if they're early in the day? Because the moon, how the moon heats up is very different from how the Earth accumulates heat, right? Earth has an atmosphere. So when the sun shines on Earth, and heats Earth up, that heat can be retained because our atmosphere will keep it in. The moon doesn't have that. So all the heat begins to radiate away, right? It starts to radiate away over time. Now, with the day being 2 weeks long, you have 2 weeks to build up all that heat, where the moon may be radiating away some of that heat, but some of it's staying or just being replaced by the constant amount of the sun hitting it. So you end up getting slightly different temperatures going on. So it wasn't extraordinarily hot because there's no air around them to heat up. It's really just the surface of the moon that's heating up, being constantly bombarded by the sun. And actually, I found that Buzz Aldrin said at one point he felt too cold inside of his spacesuit. He felt too cool. Yeah. And so he changed the thermal control unit on his suit to warm him up. Like, he felt too cold. And a lot of that is because they anticipated the fact they would be in sunlight all the time, right? As the sun is rising. And so the spacesuits are white, and that reflects all of the heat, right? White, if it's too hot, you usually wear a white shirt. Here on Earth, same thing in space. The sunlight reflects off of the white. And so it's a bit different, right? Over time, their spacesuits would warm up, and that would be a problem. So they made them white. And for their boots, they actually have 2 boots on. So they have an insulated inner boot and then an outer boot that's more layered to keep them, because they're walking on a very hot surface, essentially. Yeah, which was fun for them and very interesting. So this is kind of, we're there not at midday on the moon. We're there early in the morning, you could say. And then this is where, I guess, the terrain comes in, right? So we have this idea of where are we, time of day on the moon. Early morning, turns out it's not super hot yet because that temperature accumulates as the moon is in the sun. or the part of the moon is in the sun. And then we have to think about where we are. So the near side versus the far side, I picked this image of topography because you can kind of see, we've got where the Apollo missions were kind of around in this general areas. And then we have the South Pole. We start to get a lot more cratered. This is the South Atkin Basin, which is very very low lying ground. But we see these crater rims that end up being very high up. And this is where we start to have to think about where physically are we on the moon and how the sun shines on those places.
Right.
Which brings me to another video I wanted to show you because it was very helpful for me to understand what was going on. So this is from NASA's Visualization Studio, which I love. They have a lot of great ways of viewing different information, and it's showing the different like a simulation of what the sun's doing during the lunar day at different parts of the moon. So the top two are actual Apollo landing sites. So Apollo 16, Apollo 15. The bottom left is if we were at 60 degrees latitude on the northern part of the moon. And then the bottom right is at exactly the South Pole. And this yellow arrow is pointing at the sun. And so over the course of the lunar day, which I like that they put the galaxy in, that's also very, very fun. You have the sun rising, especially with the Apollo missions, kind of going directly overhead if you follow the arrow. But on the lunar South Pole, you have it sticking very, very close to the horizon. It doesn't go overhead the viewer. It instead just moves around them, kind of like you're being circled by the sun, which is kind of a spooky thing to think about. And if you watch the terrain, you'll notice how the shadows change because of that, right? So you get these long lying shadows at the Apollo sites as the sun rises and as the sun sets. But at the southern pole, which is what I want to focus on, you get these long shadows at all times. So it's kind of like being at the early morning constantly with these long shadows covering different parts of the terrain as the sun moves around you. It doesn't necessarily set either. It depends also on the season of the moon, which was fun to find out that the moon has seasons. I guess it would. It makes sense for it too. I just had never thought about it. The moon does have seasons, but it's not tilted as much as Earth is. Earth tilted at 23.5. The moon's tilted at about 1.5 degrees relative to the sun. It's not very much tilted at all. We end up getting this very different path of the sun and this very different view of what's happening. And different amounts of sunlight reaching different places. The moon being, the sun being directly overhead means you have the whole swath that you're standing on illuminated, whereas the moon circling low on the horizon means that there are some places that are permanently in the darkness and some places that will be permanently shadowed. So nighttime at the South Pole is going to be very different from nighttime near the equator on the moon. So that's what we need to consider with, could we survive a lunar night? Where are we on the moon that we're experiencing lunar night? Because it'll complicate things for us.
Okay. So the astronauts you went through sort of like the timeline of the Apollo astronauts. They never had to experience lunar night. They of course avoided it. And it would have been very dangerous if for some reason they had to stay there for longer, right? So if there was anything that was going wrong, they would have had to, I don't know what they would have had to do. Like, could they have survived inside of their landers?
Capsule?
Yeah.
I don't think for very long, because the problem with it getting as cold as it does is that, your body generates heat that would have also radiate away. But you're talking about like it gets to negative 200s of degrees Celsius. It gets very, very cold. And before it even reaches that point, it starts to damage equipment. So if the equipment's not built to withstand something that cold, you're going to have a lot of power failures, which comes up later because how they powered things is different from how we're anticipating to power things for Artemis. And so it wouldn't have been a great place for them to be necessarily at all. It would have been very dangerous for them to get into lunar night. Luckily, they would have had time probably to figure something out because they're there so early, right? So the idea was to get there early, both because to maximize the amount of time in the sunlight they have without it getting overwhelmingly hot, but also to kind of give them a cushion of if something goes wrong, we have time to figure it out, right? Because inside, like the LM would have been able to generate heat, like it generated its own power, which would have generated heat, but whether or not it would have lasted the full 2 weeks becomes the question. Also food, water, like it's a lot more messy.
So it's not exactly for all mankind when what's his name, was stuck on the moon for, it seemed like, almost like a year he was stuck up there, right?
Yeah, I don't know what's going on there. Like, is he in lava tubes? Because that's like a whole other thing that we could get into. I haven't seen that far, but that sounds very odd. Like a year on the moon, where are you staying?
Right. I mean, he was living in the LEM pretty much the whole
Okay,
time.
so maybe.
But we're getting off track here, because I think, like, get back to the core question is, we have rovers on the moon, and one just landed recently. Are those surviving the moon? So we're talking about humans, but can robots survive the lunar night?
So it depends on the robot. Chandrayaan-3, as far as I know, is not designed to last that long into lunar night. It's supposed to last 2 weeks or one lunar day, like two Earth weeks. Or sorry. Oh my gosh. Yeah, 2 Earth weeks, 1 lunar day. It's not necessarily designed to go through the night. There have been rovers that have survived the night. There's China's U2 rover. U2-2, the second one, has survived multiple lunar nights, and it's been okay. Its first one did survive a lunar night. I think survived 2 lunar nights, like day-night cycles, before dying due to, they think, the lunar regolith got inside and damaged a lot of the equipment along with the cold. One of the Russian rovers that they've had on the moon did not survive a lunar night because it wasn't able to close itself properly. I think it was the problem. And so the heat it was generating inside wasn't keeping the instruments warm. It was radiating away, or it was one of the solar panels couldn't close properly. And so it wasn't able to recharge itself during the day, which led to a power thing. So some of them are designed to last through the lunar night, and they'll have a mechanism that allows them to heat what they need to heat. Luckily for robots, electronics don't need to be kept as warm as human beings need to. So they have a little more wiggle room with how hot they need to keep everything going. Human beings have a preferred temperature to stay alive, right? And so, which is a lot hotter than what electronics require.
So I guess the other end of this question is, as we go forward and as we build the infrastructure on the moon, in and around the moon, is this ever going to be a possibility to have these permanent settlements on the moon? What solutions are there to solve this problem?
Well, it depends on where we're going. And in the case of the South Pole, we've got a pretty good idea of what we could do there. So this is an image of data collected over a while. It's called a time-weighted illumination map. And so it's focused on the South Pole of the moon pretty well. And it's showing over the course of time, I think it was about 6 months, 6 Earth months, to show us which parts of the moon are illuminated most of the time and which parts of the moon are in darkness. So with the fact that we have the permanently shadowed regions, which are kind of like this crater here, where it's like completely black, these areas are where it's dark pretty much all of the time, because remember, the sun is low on the horizon. So the crater rims cast those shadow in. And so it's continuously dark inside of those regions. That and the slightly tilted axis that the moon has results in those regions to be permanently shadowed, but it also results in some regions kind of being persistently illuminated, is what they say. They don't say permanently illuminated, because during a lunar eclipse, the whole part of the moon goes dark regardless. So they instead say persistently illuminated, which I thought was a very fun way to distinguish between those two concepts.
Sounds like a song title.
Persistently illuminated.
Yeah.
Yeah, it does actually. So these places in the South Pole, and I think also in the North Pole, are high enough to be continuously receiving sunlight for about 94% of the lunar year. And the longest period in some of the regions focused on, I think, near the Shackleton crater, where the longest period in shadow was only 43 hours, so just under 2 Earth days, which is pretty short considering that lunar night is typically 2 Earth weeks. And these persistently illuminated regions are adjacent or close to those large permanently shadowed areas, which are the scientific areas we want to study. And so when we look additionally at the temperature side of that, because if we're getting some sunlight, but not a lot of sunlight, and, you know, all these different things, we end up seeing minimum daytime brightness temperatures less than 238 degrees Celsius in the permanently shadowed regions. That's from the Diviner channel, the Diviner instrument, which was on the LRO. This data is from 2009. So I went and I found a model from more slightly current data. So it's a model. It's not entirely accurate because it's just modeling, and it can be slightly off. from 2010. So, a year or so later, but a bit more easier to see what's going on. That's showing what we expect those maximum and average temperatures to be around these regions. So places where they're consistently in the sun are going to be a lot warmer than places where they are permanently shadowed, right? Oh no, what does it want to show now? It disappeared on me. There it is. And so now, looking at this modeling based on different data than the 2009 model, we have the maximum and average temperatures are still very cold. So the maximum or the average temperature hottest is about negative 97 to negative 73 degrees Celsius. And the coolest average temperature goes between negative 222 to negative 213 degrees. Oh, sorry, that's in Kelvin. No, that's in Celsius. I was right. Negative 222 to negative 213 Celsius. And then the maximum temperatures they were finding to be at the hottest between 27 and 51 degrees Celsius, and at their coldest, again, between that negative 222, because it's in those craters still. And so we end up getting these interesting temperature variations. But we know that with Apollo, we were able to be okay with the temperature change with the white spacesuits, and it's not permanent. It's not there's areas where they are shadowed for at least a little bit, which would help cool things down. And we know that we're probably not going to be sending people into these craters because they're so cold. Instead, we leave that to the robotics. And so the idea, even with the Viper mission, which ties into how we power things, the Viper mission by NASA is a rover that is powered by solar panels. And its plan is that it will drive around these permanently shadowed regions, study them, come out and park itself in one of those regions that receives consistent sunlight and use that to recharge its batteries, right? So maybe that's something that we could do for when we eventually send people down to the South Pole, which ties into, how do we power things? So during Apollo, they used fuel cells to power like the LEM or the LEM, the lunar module, and some scientific instruments use solar arrays. Now, a lot of what we're seeing being put on the moon use solar arrays or some other method like fuel cells, but a lot of it seems to be headed towards this solar array version of things. They are very complex and they're very heavy, but our technology has gotten a lot better. And if we can place them in a spot where they receive, enough sunlight, maybe that is a better, it's more the cost benefit analysis tilts it in its favor as opposed to using fuel cells like we did during Apollo. But the caveat is that if they're in permanent sun all the time, it gets really hot and that can damage the arrays. And also radiation can damage them over time. So it becomes this, give and take of what could we do. But with rovers, we're seeing, well, at least with Viper, it will just park itself, charge itself, and then drive away.
Yeah. I suppose like when you're looking into the far, far future, you may envision that there might actually be like a power network that at some point they're going to have to figure out how to like transfer power in and around these different areas of the moon. If there's going to be so many countries, going, maybe even private corporations going to the moon, how they are all going to like work together, and power is going to be a big issue for them to solve.
Yeah, and it's going to look different depending on where they are. Like this was looking at the South Pole because that's where we're planning to send people. Lunar night at the equator looks very different. There's not the permanently shadowed regions at the equator. There's not the permanently illuminated regions at the equator. It's either dark or it's light. And so that's going to be very different for powering things as well when you compare the poles to the rest of the moon.
Very cool. Well, thank you, Marley. This was amazing. This was only one question that we posed for this episode. And I'm not even sure the person that posed the question in the last episode is here watching. But if you are, here is the answer to your question. Could humans survive lunar night? It would take a lot of work.
It would. It would take a lot of work. Seems like we should probably just not risk it. But,
this is fantastic. I had never even thought about this. I especially had never even thought about where the shadows run. I've seen those pictures so many times in my life. I've never even really noticed that there are so long shadows. And in every picture, all of the shadows are really long. So that is very cool. And of course, if you were out there watching and you have a question like this that you would like us to ask answer on Ask the Astronomer, we will certainly do that. We actually did get one in. We've got a few minutes left, so maybe you can give like a teaser answer to this, and maybe we'll address it in the next episode. Our next episode is going to be in 2 weeks, of course, September the 21st. We have a 19 Plus event that is also going to be that evening, Undead Stars, where we're going to be talking with Catherine Crowter from UBC, talking about her study with pulsars and how they helped with a new paper they published on new gravitational waves that they had discovered. Really, really cool stuff. So Undead Stars, which is what we're calling pulsars, these very, very old things. Lots of fun stuff at this event on September the 21st. You can go onto our website, spacecenter.ca, to get your ticket. Of course, 19 plus. So if you are an adult and would like to have a wine or beer while you listen to Marley and Catherine talk about the universe, that's going to be a very fun night. So we have that one question. We got 4 minutes left. Which might actually be a good theme for the Undead Stars. So the question from Wormy Gaming is, how did people find out, or how did they determine from the color of a star, how do they determine how hot and how bright it is? I guess there's two different things that are kind of going on there. The brightness is one thing, but how do we determine how hot a star is?
Because of its color. Yeah, no, it's kind of they're related, and so is the brightness. So the brightness or the luminosity, the temperature, and the color are all interrelated based on the age of the star and what it's currently fusing in its core and where it is in its life cycle. Hard to do in 4 minutes. Answer this question succinctly, but long while ago, a couple astronomers came up with the Hertzsprung-Russell diagram, named for someone with the last name Hertzsprung and someone with the last name Russell, who were basically doing the same thing at different times in different ways. And so this Hertzsprung-Russell diagram shows the correlation between the star's color, its luminosity, and its also its magnitude. There's 4 different things it's looking at, but they all relate to one another. And so really it was just more so we noticed a pattern going on. And once you plot it, it shows like what's happening. But that would be fun to get into in the next episode, because I talk about that a lot with kids, and then I don't think they appreciate it as much as someone who asked the question does. So
well, this is great. Maybe we're going to start a pattern. And Keith even says that he loves these speculative talks. And maybe we can even delve into a very specific question. Unless something major happens in space, we can still talk about the space news. But maybe for next episode, we're going to talk about how you determine how hot a star is.
How do we know?
I think it's always so wild, because they're tiny little dots in the sky, and astronomers study these things so far away, and they get so much information just by taking these measurements and readings. But like you said, it's not as easy to explain in 3 minutes as it might be in 20 minutes. So stay tuned for 2 weeks, September the 21st, 4 p.m. Pacific time, for another edition of Ask an Astronomer. Take care, everyone.